So what is a dot diagram? Well, a dot diagram records an object's position at a constant time interval. So it records an object's position at a constant time interval. Now, in explaining dot diagrams to you, we're going to do so mainly conceptually today. There's not going to be a lot of notes. So let's look at an example of what I mean by this. So let's say you are standing on the side of the road, okay? And you are taking photos of a car that is passing you by. So you are taking photos of a car that is passing by every second. So every second you are snapping a photo. Okay? Now, I'm going to say here that your camera is stationary.
Grade 11 students whose last names begin with L through M, please come down to the west side gym to get your photo taken. Grade 11 students whose last names begin with L through M.
So your camera is stationary. Now, if we superimpose these images, so superimposing, kind of like overlapping these photos, it's going to give you a picture of this moving vehicle. So here's my car. I'm an awesome drawer, so here's my sweet little car. And that is the first photo. So that would be, let's say, 0 seconds. Right? You take that first photo. After 1 second, the car is there. Again, we are overlapping these photos. We're sitting there on the side of the road snapping pictures, and as the car passes by, we're going to take those photos and overlap them. After 2 seconds, we're going to say the car is here. And let's say after 3 seconds, the car is here. Now, how would you describe this car's motion? How would you describe this car's motion? Yep.
As the seconds go by, it's accelerating faster each second.
Excellent. This car is speeding up. I love that you use very technical terminology there. This car is speeding up. And you're right. How do we know it's speeding up? What is happening? Every single second, what's happening? Our displacement is changing. It's getting bigger, right? So the amount of displacement, the amount of distance we are covering with every second is increasing. Therefore, our car must be speeding up. Does that make sense to everyone? Yeah? So again, the amount of distance covered is increasing with every second. And the only way to do that is if our car is traveling faster and faster and faster. So our car here is speeding up. Now, I'm kind of lazy. I don't want to draw out a bunch of cars again. So let's look at a different example. Let's say instead, let's say your car has an oil leak. Okay, it has an oil leak, and it drops a drop of oil every second. It drops a drop of oil every second. Now, looking at the drops, we get something that looks like, let's say this. Let's say we analyze the drops on the pavement, and we get something that looks just like that. How would you describe the motion of this vehicle? Now keep in mind, it's kind of pointless for me to give you this example without telling you the direction of travel. Right here, you can just intuit the direction of travel based on our car. But when I'm giving you dot diagrams, I am going to be telling you which way my vehicle is traveling. So my velocity is in that direction. So how would you describe this vehicle's motion? Ooh, good job, David. It is slowing down. Right? It is slowing down. How do you know it's slowing down?
Because the dots are getting closer.
Yeah, the dots are getting closer together, right? So the amount of distance you are covering every second is decreasing, right? The only way to make that happen is if I am slowing down. So this is a vehicle that is slowing down. Now, if it's slowing down, which direction is my acceleration? See who did their homework. So if my velocity, yeah, the opposite, good job. So if my velocity is this way, my acceleration should be that way, right? Since we are slowing down, my acceleration is in the opposite direction, right? We are slowing down. Now let's do another example where my car's dropping these drops of oil. Let's do a little bit more challenging one. Let's say we observed the oil drops on the road, and it looked something like this instead. Something like that.
Slow it down.
How would you describe the motion of that object? You're right, if it wasn't.
Slow down and sped up again.
Yeah, it's slowed down then sped up.
So they reached the red light.
If we look here, yeah, you could say it like reached a red light. We approach a stop sign maybe, right? Where our vehicle from here to here-ish, we'll say to there. What is our vehicle doing? It's not speeding up. Right, from there to there, it is going to be slowing down. I'm sorry, I forgot to point out that my velocity here, we're going to say it's in the same direction. Okay, so our velocity, our car's still traveling that way. So it's slowing down. Which means, what direction is my acceleration for this first little bit here? Yeah, it's the opposite, right? My acceleration for this first little bit is pointing that way. Now, what's happening from here to there?
Sped back.
What are we doing?
Speeding up.
Yeah, our vehicle here is speeding up. Now, if my velocity is this way, which way will my acceleration be?
The same.
Ah, good job. Lots of you did your homework. Good to see. My acceleration is that way. Right? If you are speeding up, your acceleration and your velocity are in the same direction. Now the last example I kind of want to show you here.
Grade 11 students with the last name N2O, please make your way to the West Side Gym. Grade 11 students with the last name N2O.
Now the last example I want to show you is this. So let's say we had an object that did this. Right? Our direction of travel is still that way. What would you say about this object's motion?
Keeps the same speed.
Yeah, it keeps the same speed. So what is its acceleration? What is this object's acceleration? Yeah, you're right, Evie. What is it?
0.
It is 0. Keep in mind, if my velocity is my velocity or speed here, I'm not really too particular about direction, is that going to be constant? Do we have the same speed this entire time? How do you know? How do you know that my velocity here is constant? Whew. How do we know that my velocity there is constant? Excellent. Right? Every second, we are covering the exact same distance. Right? If you are covering the same distance every unit of time, that means that your velocity must be constant. So if our velocity is constant, right, there's no change in our velocity, therefore our acceleration must be 0. Because a little refresher from yesterday, what is my acceleration? What is acceleration?
Like you're speeding up from a point.
What is, I kind of lied to you a little bit yesterday. So I said that your acceleration is speeding up or slowing down. There's actually a third form of acceleration. Because acceleration is a vector, which means what? It has a magnitude and a direction. So you have your accelerator in your car to speed you up. You have your brake to slow you down. What other control device in your vehicle do you have to cause an acceleration? Oh, excellent. You have your steering wheel, right? Changing direction is an acceleration as well. But we don't need to worry too much about that because we are mainly dealing with one-dimensional motion. So our acceleration is 0 because what is the formula for acceleration? What's our acceleration equal to? Just a little refresher from yesterday. Our acceleration is equal to my change in? Nope, change in displacement's velocity. Or change in position. It's velocity. What is the formula for acceleration?
Change in velocity over time.
Excellent. It's going to be your change in velocity over your change in time. If your velocity isn't changing, you have no acceleration, right? If your velocity is not changing, you have 0 acceleration. Now, today, we are going to be utilizing these little cars, these little electronic cars, that travel at effectively a constant speed once they have accelerated. So we're going to be dealing with a situation like this, where you have constant velocity, so no acceleration. And we're going to be feeding them through this thing here. This is a ticker tape timer. Now, the way this thing works is it oscillates up and down, and it presses on this carbon paper here. And this is going to leave little dots on a piece of paper as it's being drawn through the ticker tape timer. So it will be creating a dot diagram of that vehicle's motion. Now, the key thing...
Grade 12 students with the last names beginning with H2J, please make your way down to the west side of the gym for photos. Grade 12 students' last names with H2J.
Now the key thing with ticker tape, these ticker tape timers, is that machine oscillates with the frequency of electricity coming out of your wall. So in Canada, our frequency is 60 hertz, which means that the alternating current switches every 1/60th of a second. Therefore, this thing makes a dot every 60th of a second. So, makes a dot every 1/60th of a second. Right, and this is because that's the frequency of alternating current. Our frequency of alternating current is 60 hertz, right? That's all this machine's doing. It's just oscillating up and down with the frequency of alternating current. So you're going to be utilizing these machines today to make a dot diagram, and then I want you to calculate the velocity of your car. All of the cars have slightly different velocities, and in science, do we usually just take one result? No, what should we do? Say 3 minimum? I like that idea. We're going to do 3 minimum. So I want you to do 3 minimum samples. Don't worry, you're only going to have to do 1 strip, but on that strip, I want you to choose 3 different sections to calculate your velocity from. Now these dots are going to be pretty close together. Right, they're going to be pretty close together. So one strategy I recommend you employ today is, so if here's your ticker tape timer strip, right, and you have dots that look like this, say like this, it should be approximately looking like this, constant velocity. Now, what is the time it takes to get from this dot to this dot? I just said it. What is the time it takes? Yeah, you're right. What is it? 1/60th of a second. Now, on your tape, the dots are going to be pretty close together. And if you measure just one gap, your result will probably be fairly inaccurate because these machines aren't perfect. Okay? So what I want you to do for each of your calculations of your velocity of your car, I want you to choose a series of dots. Now, I'm going to say 6 gaps. Now, why 6 gaps? It's going to make your math nice and easy in the end, but why 6 gaps? Each of these represents 1/60th of a second. So in total, how much time has passed from here to here?
1 second.
Not 1 second. Excellent. Right? Since this is 6 1/60ths, that is 6.
Grade 12 students with the last names beginning with L through M, please make your ways down to the gym. Grade 12 students with the last names L through M, make your way down to the west side of the gym.
All right, so that is 6/60ths of a second, or you're right, Spear. That is going to be 1/10 of a second. So that is the strategy I want you to use, right? Your results will be more accurate because you're incorporating more data points. And I want you to do this 3 different times on your strip to get a more accurate representation of your velocity.